The possibility of life on Mars, or life on the closest planet to Earth, Note 1, is a subject of huge interest in astrobiology due to its proximity and similarities to Earth. To date, no proof has been found of past or present life on Mars. Cumulative evidence shows that during the ancient Noachian time period, the surface environment of Mars had liquid water and may have been habitable for microorganisms. The existence of habitable conditions does not necessarily indicate the presence of life. 1. Scientific searches for evidence of life began in the 19th century, and continue today via telescopic investigations and deployed probes. While early work focused on phenomenology and bordered on fantasy, the modern scientific inquiry has emphasized the search for water, chemical biosignatures in the soil and rocks at the planet's surface, and biomarker gases in the atmosphere. 2. Mars is of particular interest for the study of the origins of life because of its similarity to the early Earth. This is especially so since Mars has a cold climate and lacks plate tectonics or continental drift, so has remained almost unchanged since the end of the Hesperian period. At least 2/3 of Mars' surface is more than 3.5 billion years old, and Mars may thus hold the best record of the prebiotic conditions leading to life, even if life does not or has never existed there. 3, 4, which might have started developing as early as 4.48 billion years ago. 5. Following the confirmation of the past existence of surface liquid water, the Curiosity and Opportunity rovers started searching for evidence of past life, including a past biosphere based on autotrophic, chemotrophic, or chemolitho-autotrophic microorganisms, as well as ancient water, including fluvio-lacustrine environments, plains related to ancient rivers or lakes, that may have been habitable. 6, 7, 8, 9. The search for evidence of habitability, taphonomy related to fossils, and organic compounds on Mars is now a primary NASA and ESA objective. The findings of organic compounds inside sedimentary rocks and of boron on Mars are of interest as they are precursors for prebiotic chemistry. Such findings, along with previous discoveries that liquid water was clearly present on ancient Mars, further supports the possible early habitability of Gale Crater on Mars. 10, 11. Currently, the surface of Mars is bathed with ionizing radiation, and Martian soil is rich in perchlorates toxic to microorganisms. 12, 13. Therefore, the consensus is that if life exists, or existed, on Mars, it could be found or is best preserved in the subsurface, away from present-day harsh surface processes. In June 2018, NASA announced the detection of seasonal variation of methane levels on Mars. Methane could be produced by microorganisms or by geological means. 14. The European ExoMars Trace Gas Orbiter started mapping the atmospheric methane in April 2018, and the 2022 ExoMars rover will drill and analyze subsurface samples, while the NASA Mars 2020 rover will cache dozens of drill samples for the potential transport to Earth laboratories in the late 2020s or 2030s. Mars polar ice caps were discovered in the mid-17th century. In the late 18th century, William Herschel proved they grow and shrink alternately, in the summer and winter of each hemisphere. By the mid-19th century, astronomers knew that Mars had certain other similarities to Earth, for example that the length of a day on Mars was almost the same as a day on Earth. They also knew that its axial tilt was similar to Earth's, which meant it experienced seasons just as Earth does, but of nearly double the length owing to its much longer year. These observations led to increase in speculation that the darker albedo features were water and the brighter ones were land, whence followed speculation on whether Mars may be inhabited by some form of life. 15. In 1854, William Whewell, a Fellow of Trinity College, Cambridge, who popularized the word scientist, theorized that Mars had seas, land and possibly life forms. 16. Speculation about life on Mars exploded in the late 19th century, following telescopic observation by some observers of apparent Martian canals, which were later found to be optical illusions. Despite this, in 1895, American astronomer Percival Lowell published his book Mars, followed by Mars and its Canals in 1906. 17. Proposing that the canals were the work of a long-gone civilization. 18. This idea led British writer H. G. Wells to write The War of the Worlds in 1897, telling of an invasion by aliens from Mars who were fleeing the planet's desiccation. 19. Spectroscopic analysis of Mars' atmosphere began in earnest in 1894, when U.S. astronomer William Wallace Campbell showed that neither water nor oxygen were present in the Martian atmosphere. 2020, the influential observer Eugene Antoniadi used the 83 cm (32.6-inch) aperture telescope at Meudon Observatory at the 1909 opposition of Mars and saw no canals. The outstanding photos of Mars taken at the new biodome at the Pic du Midi Observatory also brought formal discredit to the Martian canals theory in 1909-21, and the notion of canals began to fall out of favor. Around this time, spectroscopic analysis also began to show that no water was present in the Martian atmosphere. Conceivably, if life exists or existed on Mars, evidence of life could be found, or is best preserved, in the subsurface, away from present-day harsh surface conditions. 47. Present-day life on Mars, or its biosignatures, could occur kilometers below the surface, or in subsurface geothermal hotspots, or it could occur a few meters below the surface. The permafrost layer on Mars is only a couple of centimeters below the surface, and salty brines can be liquid a few centimeters below that but not far down. Water is close to its boiling point even at the deepest points in the Hellas Basin, and so cannot remain liquid for long on the surface of Mars in its present state, except after a sudden release of underground water. 48, 49, 50. So far, NASA has pursued a follow the water strategy on Mars and has not searched for biosignatures for life there directly since the Viking missions. The consensus by astrobiologists is that it may be necessary to access the Martian subsurface to find currently habitable environments. 47. Cosmic radiation. In 1965, the Mariner 4 probe discovered that Mars had no global magnetic field that would protect the planet from potentially life-threatening cosmic radiation and solar radiation. Observations made in the late 1990s by the Mars Global Surveyor confirmed this discovery. 51. Scientists speculate that the lack of magnetic shielding helped the solar wind blow away much of Mars' atmosphere over the course of several billion years. 52. As a result, the planet has been vulnerable to radiation from space for about 4 billion years. 53. Recent in situ data from Curiosity rover indicates that ionizing radiation from galactic cosmic rays (GCR) and solar particle events (SPE) may not be a limiting factor in habitability assessments for present-day surface life on Mars. The level of 76 milligrays per year measured by Curiosity is similar to levels inside the ISS. 54. Cumulative effects. Curiosity rover measured ionizing radiation levels of 76 milligrays per year. 55. This level of ionizing radiation is sterilizing for dormant life on the surface of Mars. It varies considerably in habitability depending on its orbital eccentricity and the tilt of its axis. If the surface life has been reanimated as recently as 450,000 years ago, then rovers on Mars could find dormant but still viable life at a depth of 1 meter below the surface, according to an estimate. 56. Even the hardiest cells known could not possibly survive the cosmic radiation near the surface of Mars since Mars lost its protective magnetosphere and atmosphere. 57, 58. After mapping cosmic radiation levels at various depths on Mars, researchers have concluded that over time, any life within the first several meters of the planet's surface would be killed by lethal doses of cosmic radiation. 57, 59, 60. The team calculated that the cumulative damage to DNA and RNA by cosmic radiation would limit retrieving viable dormant cells on Mars to depths greater than 7.5 meters below the planet's surface. 59. Even the most radiation-tolerant earthly bacteria would survive in dormant spore state only 18,000 years at the surface, at 2 meters, the greatest depth at which the ExoMars rover will be capable of reaching. Survival time would be 90,000 to 500,000 years, depending on the type of rock. 61. Data collected by the Radiation Assessment Detector (RAD) instrument on board the Curiosity rover revealed that the absorbed dose measured is 76 milligrays per year at the surface, 62, and that ionizing radiation strongly influences chemical compositions and structures, especially for water, salts, and redox-sensitive components such as organic molecules. 62. Regardless of the source of Martian organic compounds, meteoric, geological, or biological, its carbon bonds are susceptible to breaking and reconfiguring with surrounding elements by ionizing charged particle radiation. 62. These improved subsurface radiation estimates give insight into the potential for the preservation of possible organic biosignatures as a function of depth as well as survival times of possible microbial or bacterial life forms left dormant beneath the surface. 62. The report concludes that the in situ, surface measurements, and subsurface estimates constrain the preservation window for Martian organic matter following exhumation and exposure to ionizing radiation in the top few meters of the Martian surface. 62. In September 2017, NASA reported radiation levels on the surface of the planet Mars were temporarily doubled and were associated with an aurora 25 times brighter than any observed earlier, due to a major, and unexpected, solar storm in the middle of the month. 63. UV radiation on UV radiation. A 2014 report concludes 64 that the Martian UV radiation environment is rapidly lethal to unshielded microbes but can be attenuated by global dust storms and shielded completely by less than 1 mm of regolith or by other organisms. In addition, laboratory research published in July 2017 demonstrated that UV-irradiated perchlorates cause a 10.8-fold increase in cell death when compared to cells exposed to UV radiation after 60 seconds of exposure. 65-66 The penetration depth of UV radiation into soils is in the sub-millimeter to millimeter range and depends on the properties of the soil.